Hi, we've talked about kinetic energy and its thermal energy type and its radiant energy type. Now we're going to go back to talking about stored energy. Kinetic energy is energy of movement. Potential energy is stored energy. In meteorology, the type of potential energy that we use in a lot of air movement and a lot of cloud development is called latent energy. So let's explore that type. And when we talk about that, we're talking about potential energy like the balloon that we noticed, because this is stored energy that can do work when the conditions are right. The conditions are right when I let go of it, and it goes all over the place. So that is potential energy, just like a cloud is potential energy that can let loose a tornado. Why do we call it latent energy? Latent is actually from the Latin word lato. I took five years of Latin, so I'm really into Latin. So lato means to lie hidden, to lie in wait. It's kind of like lethargy, where a person is very inactive, they're lying down, and latent, which is when a person is very secretive about their intentions, latent intentions. So that's why we call it latent energy. This latent energy is actually hidden in phase changes. Remember, Earth is the only planet that has water in all three phases. That's why we have life on this planet. The phases are solid, liquid, and gas, as you know, and that is ice and water vapor. When we say that the latent energy is hidden in the phase changes, it's something for you to consider. As ice melts, does ice change temperature? As water boils, does water change temperature? Intuitively, you may think, oh, yeah, of course. But no, the science will tell you differently. And the science will tell you differently because of latent energy. While ice is melting, it is always at 32 degrees Fahrenheit. While water is boiling, it is always at 212 degrees Fahrenheit. Let's go and look at a lot why. Latent energy changes the phase from solid to liquid, from liquid to gas. The energy is hidden in that the melting and the boiling do not change temperature of the system. So in other words, melting happens with latent energy. There's certainly energy moved into that system as it's melting, but that energy does not change its temperature. This y-axis is the temperature in Fahrenheit, unfortunately, but this shows you that the temperature during the melting phase did not change. There's still a lot of energy breaking bonds in the ice to create liquid, but the energy is being used to break the bonds. The energy is not being used to increase the kinetic energy of the system. The kinetic energy of the system does change when we add heat to the system to move it from 32 degrees Fahrenheit at the freezing level up to 212 degrees Fahrenheit at the boiling level. But once we get to the boiling level, all of the latent energy is used to break the bonds in the liquid in order to get them into a gaseous phase. And that energy that is breaking those bonds is not energy that is changing the temperature of that system. The temperature of that system drives up once all of the vapor is gone out of the tea kettle and there's no more water left to boil. To explain it again a little bit more, the latent energy changes the phase. The kinetic energy changes the temperature. You can take a look at this. This area in here is where the temperature is rising from 32 degrees Fahrenheit to 212 degrees Fahrenheit, or 0 degrees Celsius to 100 degrees Celsius. And the area here is where the temperature is rising with kinetic energy put in to go from the 100 degrees Celsius boiling point even higher and higher and higher. So that's where your kitchen fires come in. Just an aside, when all the water boils away and when the temperature rises so dramatically after all the liquid is gone and there's only vapor left. Just, you can ask me a story sometime. The x-axis here is the total amount of heat absorbed in each phase and in each change here. So this would be a phase change, this would be a phase, this would be a phase change, this would be another phase. The x-axis is the total amount of heat absorbed. When we look at that, we can describe that just as heat when we're talking about kinetic energy between phase changes. We can talk about it just as heat. But it has a special name to it when we're talking about the phase change itself. This can be known as the heat of fusion or the heat of vaporization. And what is important to remember out of here is that we measure these heats for latent energy in calories. We measure the energy here in calories. And there is quite a bit of, there's 80 calories per gram of water that's needed to go and break the bonds of ice to produce water. There's roughly 100 calories per gram of water that's needed to get the water up to the boiling point. But then what's amazing is that there is an incredible 539 calories per gram of water to get it to the point of vaporization. It takes an enormous amount of heat to vaporize water. And that is why it takes so long for water to boil. And you're sitting there and you're waiting and you're waiting and you're waiting. It takes an incredible amount of heat to get that area up to the boiling point, and then it takes even more heat to continually vaporize that off so that all of the water is converted to vapor. Heat of fusion. Think of fusion, and you might say, why is it called fusion? It's melting. Think of fusion as in jazz fusion, like you are melting together lots of different types of music to create jazz fusion. Think of nuclear fusion. You're literally melting away those atoms. So that's why it's called the heat of fusion when it's melting. It's called the heat of vaporization when you are vaporizing a liquid. Just to go back, difference between heat versus temperature. Remember, heat is energy. It can be energy throughout an object, and temperature is the measure of the average speed of the molecules within the object. Heat versus temperature. Heat is energy. That's it for latent heat. We're going to go next to transfer of latent heat. Join me there.